Billions of stars fill the Milky Way, but how did our galaxy take shape? From swirling clouds of gas to colossal galactic mergers, the story of our home is stranger than you think. In the next few minutes, we'll uncover its origins. Don't forget to like, subscribe, and share. Thank you for watching, and let's begin. The universe cools and thins after the first fire, and in the long hush that follows, matter settles into a faint pattern, printed by tiny ripples in the earliest light. Hydrogen and helium drift through a darkness that is not empty, because an invisible sea of dark matter already shapes the landscape, drawing threads and knots that soon become the scaffold of a galaxy. The background glow of ancient radiation dims toward a temperature a little above 2.5 Kelvin, carrying a map of slight temperature differences that mark where gravity will work a little harder. Gas listens to that map and moves. It falls softly toward the unseen wells, gathering along filaments, pooling in small halos, then merging again and again like dew collecting along the edges of a web. In these cool basins, atoms bump and lose energy by slow, radiative steps, and the densest pockets begin to compress further, cushioned by their own faint heat until a threshold quietly tips. The first stars appear, metal-free and enormous, blue-white and brief, their light spreading into a fog of neutral hydrogen. For the first time, the dark begins to thin. Their radiation breaks bonds, their winds stir the gas, and their deaths scatter the first heavy elements into the same wells that cradled them. The region that will one day host the Milky Way is only a slightly overdense patch in this grand weave, but in a universe ruled by patience, slight advantages compound. Along one thick filament, a train of mini-halos merges, and each merger leaves behind warmer gas and a little more carbon, oxygen, and silicon, grains that allow cooling to quicken and clouds to fragment into smaller stars. The invisible mass remains the backbone, pulling steadily indifferent to light, while ordinary matter slackens, collides, and radiates away its energy until it can settle deeper. A gentle irony rests here. It only takes a few 100 million years to prepare the stage for a large spiral galaxy, which counts as haste in cosmic accounting. Another quiet irony follows. The grand design that will guide billions of suns arises from particles that do not shine and may never be found in a laboratory. A third sits nearby. The future home of warm worlds and heavy elements begins as a place of near-perfect darkness and simplicity. The accepted picture is calm and broad. After the earliest expansion imprinted those tiny density variations, cold dark matter gathered first, forming halos whose gravity drew in gas. Star formation lit the smallest of these halos, and the energy from those first stars both nurtured and hindered further collapse, carving ionized bubbles, seeding metals, and changing the way clouds cooled. Over time, a dominant halo grew by mergers and smooth accretion along the same filaments, and that halo is the slow heart around which the Milky Way will coalesce. Within this framework, a poetic and lesser-known detail helps the mind feel the scale. The ancient background light has a spectrum nearly perfect in its smoothness, a black body curve measured on Earth with absurd precision. Yet what matters for a galaxy is not the perfection of the curve but the tiny speckles on it, temperature differences of only a few parts in 100,000 that quietly forecast where stars will bloom. The section's mystery is not hidden. The nature of the dark scaffolding remains unresolved. Whether dark matter is a particle beyond the known families, or a set of interactions not yet imagined, or a slightly different law on the larger scales, no one can yet say, and that uncertainty leaks into details of timing and structure. If dark matter collides with itself, Halos may puff and soften. If it is truly collisionless, cusps sharpen. If it is a little warm instead of cold, the smallest seeds fade. Each case would alter the earlier steps the gas takes on its way to becoming a disk and bulge. For now, the observational story allows a simple picture to stand. Halos form first, gas follows, stars begin, and feedback modulates the pace. In the forming halo that will host the Milky Way, the sounds are imagined as pressures and flows rather than literal notes. Gas streams in along one dominant filament like a slow river through a gorge, then fans into vortices as it meets the inner mass. Shocks form where infall strikes accumulated gas, converting motion into heat, and cooling lines in hydrogen and helium trace the path by which that heat leaves again. Dust grains, born in the breaths of the first dying stars, begin to help molecules form on their surfaces, making cooling more efficient. A low metallicity environment favours stars that are still somewhat massive, but no longer as extreme as the very first generation, and their lives begin to shape the chemistry of the future disk. The central potential deepens with each merger, and the angular momentum of infalling gas, imparted by tidal torques from neighbouring structures, prevents a straight collapse, creating instead an extended rotating cloud whose spin slows the plunge and spreads matter into a growing sheet. The analogy is gentle and serviceable, a long breath taken by gravity, where inflow is the inhale and radiation is the exhale, and between them the chest of the halo rises and falls across ages. Everything remains slow. A cloud crosses a kiloparsec in a handful of tens of millions of years, which is the blink of a cosmic eye and the fullness of a geological era, both true at once. Star formation rates fluctuate with the quiet violence of supernovae and the tender work of cooling lines. The outline of a disk is only the faintest premonition, a flattening of gas aligned with the direction of net spin. Around and through it, small companions continue to arrive, torn by tides, their stars strewn into long streams that will later be traced by patient telescopes. The grand picture holds steady. Gravity organizes, gas radiates, stars light and die, metals accumulate, angular momentum redistributes, and a structure begins to take shape that remembers every earlier step. The future spiral is not yet drawn, the bar not yet carved, the central black hole not yet fed to its adult mass, but the conditions that allow all of these to exist are already in place, written by invisibles and by atoms in a script of slow curves. Nothing here rushes. Only took a few 100 million years, and the universe calls that soon. The forming galaxy rests within its halo, a cocoon of dark matter that deepens quietly with time, gathering mass through a stream of mergers and a drizzle of smooth inflow. Gas follows that gravitational script, falling into the potential well but refusing to collapse directly, slowed and shaped by angular momentum. What results is not a simple sphere but a thick rotating cloud, a proto-disk wrapped in a halo of diffuse gas. This is the early foundation of the Milky Way, and even in its youth it carries the imprint of billions of years yet to come. The stars that form here do so in clusters, ignited by shocks and turbulence in the densest knots. Their light escapes into the halo, carving cavities of ionized hydrogen, a quiet architecture of bubbles that come and go as stars live and die. Each death is brief and fierce, yet its consequence is drawn out and gentle, spreading heavy elements across the forming structure. The first chemical diversity appears, though still primitive compared to later ages. Iron from supernovae, carbon from dying giants, magnesium and silicon from explosive nuclear synthesis all become part of the interstellar medium. The gas grows a little richer with each cycle, and future stars inherit that wealth, A soft irony is visible. The Milky Way begins not with an elegant spiral, but with a chaotic soup of clumps and flows, a messy workshop that only much later will smooth into symmetry. Another irony lingers. The path toward calm, ordered beauty requires the chaos of violent star deaths, explosions that inject disorder yet ensure chemical fertility. A third irony is more subtle. The future of stable planetary systems relies on a past that knew only turbulence and destruction. Fact remains steady. Cosmological simulations and observations suggest that galaxies like the Milky Way grow by accreting smaller systems, a process known as hierarchical assembly. Evidence is written today in stellar streams, long threads of stars pulled from ancient dwarfs that merged with the halo. These relics confirm the messy beginnings. A lesser-known poetic detail helps anchor the picture. In the outer halo, globular clusters form, dense spheres of ancient stars that will survive for billions of years. Each cluster holds hundreds of thousands of suns, bound so tightly they orbit one another for eons, witnesses to the earliest conditions of the galaxy. They are fossils, glowing archives of a time when star formation proceeded differently, creating systems far denser than most that followed. The mystery sits nearby. How exactly the Milky Way's earliest proto-galaxy merged with others is not fully reconstructed. Stellar archaeology tells fragments, chemical abundances hint at origins, and simulations provide plausible histories, but the exact sequence of mergers remains blurred. The Gaia mission has traced remnants of one major ancient collision, the so-called Gaia Sausage Enceladus event, but whether that was the defining formative merger or only one in a series is still uncertain. In this ambiguity rests the reminder that our home galaxy is at once a specific object and a typical one, both unique and general. Gas continues to cool, condense and rotate. Turbulence stirs it, supernovae heat it, and gravity pulls it back again. The cycle of star formation and feedback finds a rhythm, though irregular, marked by bursts and lulls. Each wave of new stars lights the protodisk and thickens it. Outflows rise like smoke from the galactic plane, fountains of hot gas that rain back after cooling, a galactic circulation system that mixes metals and redistributes energy. At the center, a denser region gathers mass faster than its surroundings. Here, conditions are ripe for the formation of a massive black hole seed, born from either the collapse of a supermassive star or the direct infall of dense gas. This seed will eventually grow into Sagittarius A, the central black hole, though for now it is only a faint presence, its future influence hidden. The shape of the galaxy becomes more defined. A bulge of stars swells at the center, a thick structure supported by random orbits, while the disk flattens further with each rotation. Angular momentum dictates this order, conserving spin while redistributing energy, slowly pressing the gas into a plane. Spiral arms are still absent, but the raw potential for them already lies in the density waves that ripple through the disk. A gentle analogy fits. The proto-galaxy breathes as a great chest of gas and stars, each burst of star formation a sharp inhale, each supernova-driven outflow a long exhale. Over hundreds of millions of years, this breathing reshapes the halo into a layered body, with a central bulge, a developing disk, and a diffuse envelope. Streams of stars from shredded companions add texture, tracing faint arcs through the outer reaches. They are the scars of assembly, yet in their faintness they also provide beauty. The tempo remains impossibly slow. A cloud of gas needs tens of millions of years to fall into the disk, collapse into stars, and then recycle its atoms into the interstellar medium again. What seems to us as sudden, like a starburst, is to the galaxy only a passing weather front. Only took 1 billion years to build the basic structure, and in cosmic terms that counts as ordinary. The halo already extends hundreds of thousands of light years, while the disk spreads to tens of thousands. The stars forming here are more metal-rich than the earliest generation, but still poor by the measure of today. Some will survive into our own time, orbiting in the thick disk or halo as ancient witnesses. Others will explode quickly, their metals locked into new dust and molecules, enriching the gas that will one day form the Sun. The formation is neither tidy nor abrupt, but it is unbroken. Piece by piece, stream by stream, burst by burst, the Milky Way takes on its broad shape. The interplay of dark matter scaffolding, gas cooling, stellar feedback, and tidal mergers all contribute, each process essential. The mystery of how precisely these influences combined remains unsolved, but the broad arc is clear. Our galaxy is the sum of countless quiet accidents, each small in the moment, each decisive in hindsight. The symmetry we admire today was never inevitable. It is the product of patient gravity and restless feedback, finding a balance across billions of years. In that balance lies the calm order of the spiral arms, still unborn in this epoch, waiting in the future. For now, the forming Milky Way is a hazy, luminous cloud threaded with star clusters, lit by hot gas, and surrounded by streams of ancient mergers. Its shape is not yet the graceful disk we recognize, but its essence is already decided. The structure is seeded, the rhythm established, and the galaxy's long unfolding has begun. The thickening of the galaxy proceeds slowly, a process not of sudden design but of accumulation. The proto-Milky Way swells with each merger, drawing in smaller galaxies and their stars, gas, and dark matter halos. These events are not rare intrusions but the very mechanism of growth, for without such steady consumption the galaxy would remain a modest cloud. Each merger leaves behind both disruption and order. The disruption shows as streams of stars stretched into elongated ribbons by tidal forces, and those streams still encircle the galaxy today, fossil reminders of long-vanished companions. The order comes from the way gravity redistributes angular momentum, feeding the growth of a central bulge and flattening the disk. In this balance of destruction and assimilation, the shape we recognize begins to sharpen. Gas is the most obedient to gravity, for it radiates energy as light and can settle into new structures. As clumps of gas from satellites fall into the main halo, they collide, shock, and lose motion, spiraling down into the developing disk. Stars are less forgiving, for they cannot radiate away their orbital energy. They remain in elongated orbits, swelling the halo or forming a puffed-up thick disk. In this way, the Milky Way gathers multiple layers of stellar populations, each recording the conditions of its birth. A quiet irony is present. The graceful flatness of a galactic disk requires the rough violence of mergers and collisions. Another irony rests nearby. Stars that live in serene orbits today were once born from chaotic, turbulent gas clouds that collapsed under duress. A third irony: the bulge at the center, often seen as a sign of age and stability, is built largely from the scattering of stars that once belonged to smaller galaxies. The facts align with simulations and observations. Galactic disks do not emerge pristine but are assembled through hierarchical processes guided by dark matter. The thick disk of the Milky Way, containing stars more than 10 billion years old, is believed to be the relic of early chaotic mergers. The stellar halo, diffuse and extended, holds debris from many smaller systems. Globular clusters, dense knots of ancient stars, orbit through this halo as reminders of a more crowded epoch. The bulge is enriched, its stars showing a wide spread of metallicities that record both rapid early star formation and subsequent infall. The poetic detail is this. In the darkness of the outer halo, faint streams of stars wrap around the forming disk, invisible to the naked eye but revealed by long patience and sensitive instruments. These streams are like ghost rivers, flowing across the galactic sky, tracing paths that began in dwarfs torn apart billions of years ago. They're delicate, almost invisible, yet they carry the weight of entire histories. The quiet mystery remains in the question of sequence. Which mergers were decisive, and how many? The Gaia mission has mapped one major ancient collision, the Gaia Sausage Enceladus event, which brought stars into the halo and stirred the disk. Yet the precise order of events remains hidden in overlapping orbits and blended chemical signatures. Did one great merger set the thick disk in motion, or did many smaller ones conspire together? The answer is not yet known, and perhaps it never will be fully disentangled. Gas continues to fall inward, cooling through emission lines of hydrogen, helium, and the trace metals created by earlier generations of stars. The disk becomes denser and flatter, a rotating sheet tens of thousands of light years across. Within it, turbulence organizes into spiral-like waves, not yet the grand arms of maturity, but hints of the pattern to come. The gravitational potential deepens as mass accumulates, and orbits within the disk align into a more coherent rotation. Angular momentum ensures that collapse never finishes. Instead, the disk spreads outward, its stars tracing ordered circles. At the center, mass builds faster. The bulge grows, supported by random orbits, and the central black hole seed accretes gas, swelling slowly though still far from the mass it will one day achieve. Outflows from supernovae and active star clusters pump gas into the halo, fountains that rain back after cooling. This circulation stirs the chemistry of the interstellar medium, mixing metals and distributing energy. The cycle repeats endlessly. Gas cools, stars form, stars die, metals spread, gas cools again. A gentle analogy fits the rhythm. The galaxy is like a great wheel slowly finding its balance, each spoke forged by mergers, each rim smoothed by rotation, each hub deepened by collapse. The wheel turns not in minutes but in hundreds of millions of years, and each revolution changes the pattern slightly, settling it into greater coherence. Star formation rates fluctuate, but the overall trend is toward order. The thick disk transitions gradually to a thinner one as gas settles into more stable orbits. The chemical enrichment rises. Stars form with increasing fractions of heavier elements, preparing for the distant possibility of planets. Already, the seeds of later solar systems lie in the ashes of massive stars. It only took 1 billion years for these conditions to arise, a brevity in cosmic time yet unimaginable in human reckoning. Another irony emerges in reflection. The stability of planetary systems billions of years later depends on the chaos of mergers and the generosity of supernovae. The developing Milky Way continues to absorb dwarfs. Some are shredded entirely, their stars dispersed into streams. Others survive as satellites, orbiting for billions of years before their fates are decided. The large and small Magellanic Clouds visible to us today are among the survivors of this process, still interacting with the Milky Way and shaping its outskirts. Each companion galaxy is both separate and part of the whole, feeding gas, stirring tides, and leaving trails. The assembling disk becomes more luminous as star formation continues. Massive blue stars shine brightly but die quickly, while smaller red stars endure, accumulating as a long-lived population. the balance shifts towards stability. The galaxy begins to resemble the shape we know, though still rough around the edges. Spiral arms are still faint, the bar is absent, and the halo is crowded with debris. Yet the essential symmetry of a disk galaxy is written into its rotation. This is the quiet culmination of the first major stage of assembly. What began as a turbulent cloud drawn from filaments has become a layered structure. A halo of streams and clusters, a bulge of old stars, and a disk in the process of flattening. The Milky Way is no longer only a proto-galaxy. It is a young spiral, still growing, still colliding, but unmistakably shaped by the laws that will guide its next billions of years. The Milky Way drifts through its youth with the quiet inevitability of gravity, slowly refining its form as billions of years pass. The galaxy that was once a turbulent cloud now shows the growing balance of a rotating disk, though the process remains uneven. Gas streams in along filaments from the cosmic web, feeding the halo and sustaining star formation. Each inflow is not a flood but a patient river of hydrogen, sometimes cool, sometimes heated by shocks, sometimes enriched with metals from neighbouring systems. As it arrives, it mixes with the disk, stoking the birth of stars. Star formation spreads in clumps, ignited where gas density peaks, glowing in associations and clusters that shine for a brief cosmic moment before dispersing. The most massive stars live only a few million years, pouring out radiation, carving cavities, and dying in brilliant explosions. Their remnants enrich the gas with heavy elements that will later form rocky planets and complex chemistry. In this way, the galaxy's evolution is both violent and delicate, destruction and creation woven together seamlessly. A quiet irony reveals itself. The seeds of stable worlds require the instability of stellar deaths. Another irony lies in the fact that order in the disk emerges only because chaos redistributes angular momentum. A third irony is that the thinness of the galactic plane, so serene to an observer, is maintained by countless collisions, shocks, and outflows. The scientific consensus describes these processes clearly. The galaxy's disk grows as infalling gas cools and settles into rotational equilibrium. Stars form more efficiently as metallicity increases, because molecules and dust provide faster cooling. Feedback from supernovae regulates this cycle, preventing runaway collapse and ensuring that star formation continues gradually over billions of years. Simulations show that without feedback, galaxies would burn through their gas too quickly. A poetic detail emerges in the outer halo. There, stars orbit in elongated paths far from the galactic centre, some belonging to streams of ancient dwarfs, others to globular clusters that formed at the dawn of time. These distant lights circle in silence, tracing loops hundreds of thousands of light-years wide, so faint that they would be invisible without careful measurement. They are the whispers of the galaxy's youth, continuing their motion even as the disk evolves far below. The quiet mystery remains in the precise origin of the spiral pattern. Spiral arms are not fixed structures but density waves, regions where stars and gas bunch together temporarily as orbits converge. Yet the exact mechanism of their persistence is still debated. Do they arise spontaneously from instabilities in the disk, or are they maintained by interactions with companions, or perhaps both? The Milky Way's spiral structure appears stable, yet the physics of that stability is not fully resolved. Meanwhile, the central region grows denser. The bulge thickens with older stars whose orbits are randomized by past mergers. At its heart, the black hole seed begins to accrete more material, fed by streams of gas and star clusters drawn inward. Sagittarius A remains small compared to its future size, but even now it shapes its surroundings, heating and stirring nearby gas. Occasionally it flares, brief outbursts of radiation from matter falling into its event horizon, leaving behind traces that can still be read in X-rays today. Around the bulge, the disk flattens further. Rotation aligns the orbits of stars, pressing the structure into a plane tens of thousands of light-years across. Within the plane, gas organizes into lanes that will eventually seed spiral arms. Dust clouds gather, cooling further and fragmenting into dense molecular regions. These clouds become cradles of star formation, where clusters are born, many of which dissolve within a few 100 million years, leaving their stars scattered across the disk. Some clusters survive longer, their bonds tighter, their stars circling together for billions of years. The galaxy is a collection of these layers, each process contributing to a broader harmony. A gentle analogy comes to mind. The Milky Way is like a vast loom, weaving threads of stars and gas across its disk. Each merger, each supernova, each inflow of hydrogen is another thread, and gravity is the shuttle that pulls them all into a pattern. The loom works slowly, its cloth stretching across billions of years, yet the fabric it creates is coherent, strong, and luminous. The cycle continues with patience. Gas falls in, stars ignite, metals spread, outflows rise, gas cools, and the sequence begins again. Over time, the disk becomes chemically enriched enough that stars like the Sun become possible. This enrichment is uneven. Higher in the inner disk where star formation is more active, lower in the outskirts where gas is still pristine. The gradient reflects the history of the galaxy, written in chemistry as well as in light. In the halo, dwarf galaxies continue to arrive. Some are stripped of their stars and gas, leaving tidal streams. Others remain intact, orbiting as satellites. The large and small Magellanic Clouds, though still far in the future of this narrative, are part of this long tradition of companions, shaping the Milky Way through their tides and feeding its halo with their debris. These interactions are both gentle and decisive. They stir the disk, generate waves, and sometimes trigger new star formation. The tempo remains slow, measured in hundreds of millions of years. A single orbit of a star at the edge of the disk takes more than 200 million years, a span that covers the rise and fall of entire planetary systems elsewhere. To the galaxy, it is only one turn of a wheel. In that span, countless stars live and die, countless clouds collapse and disperse, countless mergers deposit new material. Only took 2 billion years for the disk to take recognizable form, a fact that to the universe is trivial, but to us unfathomably long. Another irony emerges in reflection. The galaxy is at once restless in detail and utterly calm in its overall form. The violence of starbursts, the fury of supernovae, the disruption of mergers all coexist with the grand serenity of a spiral disk that persists unchanged to the eye across eons. The Milky Way's quiet symmetry hides the storm of processes that sustain it. The narrative of this epoch is one of balance. Gas inflow and outflow remain in equilibrium. Star formation and feedback sustain one another. Growth by mergers continues but slows compared to earlier times. The galaxy enters a phase of long refinement, a steady unfolding that will last for billions of years. Its form is now clear. A central bulge, a rotating disk, a halo of streams and clusters, and a dark matter skeleton that holds it all together. The Milky Way is young by cosmic standards, but it is already recognizable as itself. The stage is set for the next chapters, in which spiral arms will emerge more clearly, the central bar will grow, and the black hole will mature. For now, the galaxy rests in quiet balance. a luminous disk suspended in darkness, its shape still forming, its destiny already written by the invisible pull of gravity and the luminous deaths of stars. The Milky Way turns slowly through the dark, a wheel of stars and gas suspended in the silent depth of the universe. Its disk is more defined now, a broad sheet tens of thousands of light-years across, rotating with patient steadiness. Within that disk, the first outlines of spiral arms begin to show. They are not rigid structures, but gentle waves of density, compressing gas as they move through it, allowing new stars to form along their crests. Bright young clusters outline these arms, their blue light tracing patterns that shift over hundreds of millions of years. The spiral is a process, not a shape. Yet to the distant eye it looks like a grand design. The fact remains that spiral arms are waves, not permanent features, and their persistence is a matter of ongoing debate among astrophysicists. Whether they are long-lived density waves or recurrent patterns stirred by interactions, their presence in the Milky Way is unmistakable. A quiet irony follows. The elegant spirals we admire are not fixed but transient, constantly reformed by motion and instability. Another irony is that the arms, symbols of order, are maintained by the disordered motion of stars and gas. A third irony lies in the fact that spiral arms nurture star formation, yet the massive stars they create quickly die and vanish, erasing the very brightness that mark the arms. The galaxy's bar is not yet fully grown, but hints of it appear at the centre. Bars arise from instabilities in rotating disks, where stars redistribute angular momentum and funnel gas toward the core. This slow migration builds both the bar and the central bulge. The bar will one day shape the Milky Way's inner structure, but for now it is only beginning, a faint elongation in the stellar distribution. At the core, Sagittarius A continues its quiet growth. Gas and stars drawn inward feed the black hole, increasing its mass. Periodically it flares as matter falls across the event horizon, releasing bursts of radiation. These episodes are brief compared to cosmic time, but their signatures remain in bubbles and arcs of hot gas that expand outward. Even at this early stage, the black hole influences the central region, though its gravity is strong only near the heart. Far beyond the core, the halo remains diffuse and immense. It holds streams of stars from past mergers, each stream stretching thousands of light years. They weave a ghostly net around the galaxy, nearly invisible but carrying the memory of systems long absorbed. Globular clusters orbit in this halo as well, dense spheres of ancient stars, some among the first to form. Their tight orbits and great ages make them witnesses to the earliest chapters of the Milky Way's story. They are fossils in motion, glowing archives of a youth already billions of years past. Gas dynamics continue to shape the disk. Inflows from the halo replenish the star-forming regions, while outflows from supernova heat and expel gas into fountains that rise and fall across the galactic plane. This circulation maintains balance, preventing star formation from consuming gas too quickly. Without it, the galaxy would burn through its reserves and fade prematurely. Instead, the Milky Way sustains itself, a self-regulating system where creation and destruction are intertwined. A poetic detail emerges in the motion of stars within the disk. They orbit not as a rigid body but with differential rotation, inner stars circling faster than those farther out. This shearing motion stretches patterns, winding them over time, yet it also maintains the coherence of the spiral arms. The galactic rotation curve, measured billions of years later, reveals a mystery. Instead of declining at large radii as expected from visible matter alone, the rotation speed remains flat, pointing to the presence of dark matter. The quiet mystery remains unresolved. The nature of dark matter The unseen mass that anchors the galaxy continues to elude detection. Whether it is a particle, a field, or a sign of altered gravity, its role in shaping the Milky Way is undeniable. The halo of dark matter is the true skeleton of the galaxy, vast and invisible, dictating the motions of stars and gas. Without it, the disk would not hold together. With it, the Milky Way remains stable across billions of years. The cycle of star formation proceeds at a steady pace. Gas clouds collapse into clusters, massive stars ignite, radiation and winds disperse the surrounding gas, and supernova scatter heavy elements. These cycles enrich the interstellar medium, gradually raising the metallicity of new stars. The inner regions, where star formation is most active, become chemically rich first, while the outer disk lags behind. This radial gradient will persist into the present, a chemical map of the galaxy's history. A gentle analogy compares the process to a cosmic orchard. The galaxy plants seeds in the form of gas clouds, nurtures them into clusters, harvests their light, and then recycles their ashes as nutrients for the next generation. Each cycle enriches the soil, allowing new forms of growth. The orchard does not end, but continues season after season, generation after generation. The disk's structure becomes thinner as time passes. The thick disk, formed in early mergers, is joined by a thinner disk of stars born from more settled gas. This layering creates distinct stellar populations, their ages and compositions different, their motions reflecting the turbulence or calm of their birth environments. To astronomers billions of years later, these populations will tell the story of the galaxy's formation. To the galaxy itself, they are simply layers of growth. The Milky Way's companions play their part as well. Dwarf galaxies orbit in the halo, some feeding gas and stars into the main disk, others waiting for their eventual absorption. Each interaction stirs the disk, creating waves and ripples that pass through the stellar sea. These disturbances trigger new star formation, adding brightness to the spiral arms. The galaxy is not an isolated island, but part of a larger community, its shape influenced by neighbours and companions. The timescale remains vast. A single orbit of the Sun's future position around the galactic centre takes more than 200 million years. In that span, continents can drift, species can rise and fall, civilizations can appear and vanish, and the galaxy notices none of it. Its rhythm is slow, steady and patient, unbothered by the details of individual stars or worlds. Only took 2 to 3 billion years for the Milky Way to acquire its broad features, a brevity to the cosmos, yet a span beyond imagining for human minds. Another irony emerges in reflection. The stars that make the galaxy luminous are also the ones that die quickly, while the long-lived faint stars, though nearly invisible, form the true backbone of the disk. The beauty of the Milky Way's glow is provided by the briefest lives, while its persistence rests on the dimmest. The galaxy now resembles itself more clearly. A bulge at the centre, a flattening disk with faint arms, a halo filled with streams and clusters, and an invisible skeleton of dark matter holding it all together. It is still young, still evolving, but its identity is fixed. It is the Milky Way, a spiral galaxy of growing elegance, shaped by time, gravity, and the quiet cycles of birth and death among the stars. The Milky Way rotates calmly, its disk more ordered than before, though the processes that shape it remain restless. Stars continue to form in dense molecular clouds, scattered through the spiral arms, their blue light marking the ridges of higher density. Between these arms lie quieter stretches where older stars drift, less luminous but longer lived. The balance between young and old, between bright and dim, defines the galaxy's glow. Each cluster of massive stars burns intensely, then ends in explosions that return metals to the gas. These explosions ripple through the disk, compressing other clouds and sparking new generations. The cycle repeats endlessly, creation and destruction interwoven without pause. A fact remains clear. The Milky Way sustains star formation through a steady inflow of gas from its halo and from captured dwarfs. Without this inflow, the disk would consume its reserves and star formation would decline. Observations of nearby galaxies confirm that gas accretion is vital for long-term activity. A poetic detail lies in the way this inflow sometimes appears as high-velocity clouds, streams of hydrogen moving faster than the disk's rotation, descending like gentle rivers from the halo. They are invisible to human eyes, yet radio telescopes reveal their quiet descent, sustaining the galactic cycle. The quiet mystery remains in the question of longevity. How long can the Milky Way sustain its spiral arms? Some simulations suggest they are transient, regenerated by interactions and instabilities. Others propose they may persist as long-standing waves. The truth is still debated, and the spiral's endurance remains an open question, one that lingers like a faint uncertainty over an otherwise familiar structure. 3 soft ironies emerge in this chapter. It only took a few billion years for the galaxy to appear majestic, yet its beauty is fragile, dependent on the turbulence of gas. The graceful spiral arms, admired as symbols of order, are sustained by instability. The steady glow of the galaxy comes not from stability, but from constant recycling, a system in which permanence is built from impermanence. The bulge at the centre grows denser as orbits scatter. Stars of many ages coexist here, some formed in rapid bursts early on, others delivered by mergers, still others born from gas funneled inward by the developing bar. The bar strengthens slowly, stretching across the central region, guiding gas toward the core. This migration of gas fuels star formation in the bulge and feeds the black hole at the very centre. Sagittarius A continues to grow, still modest in scale compared to its eventual mass, but significant enough to shape its immediate environment. Periodic outbursts from accretion leave traces in the surrounding gas, faint bubbles and filaments that persist as records of its activity. The halo continues to receive new arrivals. Dwarf galaxies approach on long, slow orbits, sometimes stripped of their gas before merging, sometimes feeding gas into the Milky Way. Their stars stretch into streams that wrap around the galaxy. These streams are not temporary scars, but long-lasting features, remaining coherent for billions of years. They testify to the galaxy's past, each one a remnant of an encounter that shaped the halo. Globular clusters still orbit in the halo as well, dense with ancient stars, glowing spheres that refuse to dissolve despite tidal forces. They are resilient fossils, bearing witness to the earliest phases of galactic formation. A gentle analogy can be made. The Milky Way is like a vast lake into which rivers flow and from which vapours rise, with clouds condensing above and rain falling back down. Gas flows in, stars form, outflows rise, and then the cooled material returns. The lake remains full because the cycle is balanced, yet each drop of water has its own brief journey. So too with the galaxy, which remains luminous and alive because its parts are always changing. The disk becomes more chemically complex as metals accumulate. Each new generation of stars forms from gas enriched by its predecessors. In the inner disk, metallicity grows faster, allowing the future possibility of rocky planets. In the outer regions, enrichment is slower, leaving stars poorer in heavy elements. This chemical gradient maps the galaxy's history, a subtle record written in starlight. The tempo remains vast. A single rotation of the Sun's future orbit still takes more than 200 million years, and in that span entire cycles of life and death among massive stars unfold. The galaxy notices none of it. Its rhythm is steady, unchanging to the eye even as every detail is in flux. Only took 4 billion years for the Milky Way to reach a state of relative maturity, which is a blink in cosmic time yet beyond comprehension for human reckoning. Another irony emerges. The luminous disk that seems so stable is always on the verge of transformation, each generation of stars altering the chemistry, each merger altering the structure. Stability itself is an illusion, a product of vast timescales that smooth over the turbulence. The arms continue to sweep around the disk, compressing gas, forming stars, fading and reforming. The bar strengthens, elongating across the central bulge. The halo continues to hold its streams and clusters. The dark matter skeleton remains invisible but indispensable, anchoring the motions of every star. In all of this, the Milky Way is not unique. Other spiral galaxies across the universe follow similar patterns, each shaped by gravity and time. Yet for us, this one is singular, for it is our home, the place where every atom in our bodies was forged and every history unfolded. The galaxy now rests in balance. Gas inflow sustains star formation. Supernovae enrich and regulate the medium. Spiral arms and the bar guide the structure. The bulge swells, the halo endures, and the black hole waits. The Milky Way is not yet old, but it has passed through its youth. Its shape is secure, its rhythm established, its future written in the same forces that brought it here. The Milky Way glides forward in time, its spiral arms more distinct now, marked by luminous ribbons of blue stars and threaded with dark lanes of dust. These arms are places of constant renewal, where molecular clouds collapse and new stars ignite. The oldest stars, dim and red, drift through the background, while the youngest shine briefly and die, leaving behind remnants that feed the cycle again. In this way, the arms are both nurseries and graveyards, maintaining their brightness only because their brightest stars vanish quickly. A fact holds steady here. Spiral arms are not fixed entities but patterns of density that move through the disk. Gas enters the pattern, is compressed, and forms stars, while the stars themselves drift out, leaving the arms outlined by successive generations. This process ensures the arms persist, though no individual star remains bound to them. A poetic detail lies in the presence of great star-forming regions, immense nebulae that glow in red emission from ionized hydrogen, their shapes sculpted by radiation and winds. They are temporary sculptures, dissolving in tens of millions of years, yet in their brief span they illuminate the structure of the arms. The mystery continues in the precise origin of spiral structure. Some argue for long-lived density waves, others for recurrent transients triggered by perturbations. The Milky Way's arms may be influenced by both, stirred by the gravitational pull of satellite galaxies while sustained by internal dynamics. The details remain unsettled, and in that uncertainty the arms gain a layer of enigma. 3 ironies settle softly into this chapter. The arms that seem permanent are endlessly transient. The glowing blue stars that define them are already doomed to short lives. The regions that look like beacons of stability are maintained by constant instability. The central bar strengthens further, extending across the bulge. Bars act as engines of evolution, driving gas inward along their length. That gas feeds starbursts near the center, creating clusters of young stars even in the crowded bulge. Some of this gas spirals closer still, adding mass to Sagittarius A, which grows in silence. The black hole rarely flares dramatically, but when it does, it leaves faint imprints in the surrounding medium, arcs of heated gas that persist long after the flare itself is gone. The bulge itself remains complex, populated by old stars of many metallicities. Its stars are less ordered than those in the disk, their orbits randomized by earlier mergers and by the bar. The bulge is a crowded archive, recording the chaotic beginnings even as the disk settles into order. In the outer halo, new streams of stars appear as dwarf galaxies fall in. Some streams are broad and diffuse, others narrow and sharp, each one a record of a merger. They wrap around the galaxy in great loops, moving slowly, stretched by tides. Their persistence is remarkable. Billions of years after the merger they remain visible, tracing orbits that recall events long past. Globular clusters continue their motion through the halo. They are ancient survivors of the earliest phases, each containing stars more than 10 billion years old. Their dense cores resist tidal disruption, allowing them to endure where looser systems would dissolve. They orbit silently, their age is a reminder of the deep past that shaped the galaxy. A gentle analogy presents itself. The Milky Way is like a vast clock, with stars as its hands, arms as its gears, and gravity as its mechanism. The hands turn at different rates, the gears shift and settle, yet the clock keeps time across billions of years. Its ticking is slow, almost imperceptible, but relentless. The chemical story deepens. Each generation of stars enriches the interstellar medium, raising metallicity in the inner disk and spreading it outward. The elements necessary for planets, iron, silicon, oxygen, carbon, accumulate. In the inner regions, where star formation is more intense, metallicity grows faster. In the outer disk, progress is slower, leaving populations of metal-poor stars. This gradient is a quiet record of the galaxy's evolution, etched into the chemistry of stars. The timescales remain immense. A single orbit at the Sun's distance takes more than 200 million years, and in that span stars are born, die, and recycle their atoms into new generations. The galaxy turns slowly, yet every moment is filled with change. Only took 5 billion years for the Milky Way to reach a state where spiral arms, bar, bulge, and halo all coexist in relative balance. To the universe, this is ordinary. To us, it is beyond comprehension. Another irony arises. The galaxy appears still to the eye, yet it is never at rest. Every cloud moves, every star orbits, every arm shifts. What seems permanent is only the sum of countless motions. The arms continue to sweep through the disk. The bar channels gas inward. The halo maintains its streams. The black hole grows slowly, nearly invisible but always present. Dark matter holds the structure together, unseen but essential. The Milky Way now resembles the galaxy we know, though younger and still more turbulent. Its disk shines with billions of stars. Its bulge glows at the center. Its halo stretches wide, filled with faint structures. Its future remains long, but its shape is already clear. A galaxy that began as a faint overdensity in the early universe is now a grand spiral, luminous, ordered, yet always in motion. The Milky Way drifts deeper into its maturity, its spiral arms bright with young stars, its bulge crowded with ancient ones, its halo wide and faint. The galaxy has reached a stage where its overall shape changes slowly, but within that apparent calm every part remains alive with motion. Stars circle the center in orbits that never end, gas clouds collapse into clusters, supernova blast apart their surroundings, and the black hole at the core waits quietly, occasionally flaring when it is fed. What to the distant eye appears serene is in truth a system of endless flux, a balance of forces that repeats across billions of years. Fact remains at the center of this epoch. The Milky Way is a barred spiral galaxy, with a central bar funneling gas inward, a bulge of stars older than 10 billion years, a thin disk filled with younger populations, and a halo extending outward hundreds of thousands of light years. Dark matter holds all of this together, its mass outweighing the visible stars and gas by a factor of 5 or more. Without it, the spiral arms would unwind, the disk would disperse, and the galaxy would not exist in recognizable form. A poetic detail rests in the faint glow of the thick disk. Its stars are not as bright as the young clusters in the arms, but they form a dim, even light that surrounds the thin disk. They are ancient relics of early times when mergers stirred the gas and created stars with little chemical richness. They remain in place, orbiting above and below the galactic plane, like a shadow of history suspended around the bright present. The quiet mystery lies in the role of the bar. Bars are thought to drive secular evolution, moving stars and gas, shaping the bulge and the inner disk. Yet their lifetimes and origins are not fully understood. Do bars persist for billions of years, or do they dissolve and reform? In the Milky Way, the bar seems long-lived, but the physics of its persistence remains uncertain. The first irony appears here. The bar that stabilizes the galaxy's inner structure is itself a sign of instability in the disk. The second irony follows. The bulge, so crowded and old, is partly built from stars that migrated inward, not only from the galaxy itself but from dwarfs long consumed. The third irony rests in the fact that what we see as calm order, the spirals, the bar, the bulge, is maintained by constant disruption, mergers, collisions, and feedback. The black hole at the center grows steadily. Its mass increases by swallowing gas and stars drawn close, though it spends much of its time quiet. Occasionally it brightens, emitting radiation as matter falls into its horizon. These episodes heat and stir the surrounding medium. Later, evidence of ancient outbursts will be visible as giant gamma-ray bubbles extending far above and below the plane, silent records of energy released millions of years ago. Around the bulge, the bar drives gas into star-forming rings, feeding bursts of activity even in the dense core. In the disk, spiral arms remain the dominant sites of star formation. Clouds collapse into clusters, clusters shine and disperse, and their remnants enrich the gas. Dust lanes trace the arms, cold and dark yet essential, for they shield molecules that enable further collapse. The galaxy is an ecosystem of recycling. Gas becomes stars, stars enrich gas, and the cycle continues without pause. A gentle analogy can be drawn. The Milky Way is like a great breathing organism. Gas inflows are the inhale, supernova outflows are the exhale, star formation is the beating heart, and dark matter is the skeleton that holds it all. The rhythm is slow but steady, and each breath lasts millions of years. The halo holds its quiet witnesses. Streams of stars continue to orbit, stretched remnants of long-lost dwarfs. Some streams are nearly invisible, others bright enough to trace with future telescopes. Globular clusters still circle, glowing knots of ancient suns, their densities so high that stars pass within a light year of one another. They are fossils of the galaxy's youth, unchanging even as the disk below evolves. The chemical enrichment of the disk grows more complex. By now, stars with higher metallicity form regularly, particularly in the inner disk. Their compositions include all the elements needed for rocky planets and complex molecules. The outer disk lags behind, its stars poorer in heavy elements, a record of slower star formation. The chemical gradient persists, a quiet archive of how different regions of the galaxy grew. The timescales remain immense, One orbit at the Sun's radius still takes more than 200 million years. In that time, continents could drift across a planet, oceans could rise and fall, species could appear and vanish. The galaxy, indifferent, continues its rotation, unchanged in its grand form though every detail moves. Only took 6 billion years for the Milky Way to achieve its present elegance, which in cosmic time is no more than an early chapter. Another irony emerges here. The stars that give the galaxy its glow are only a fraction of its true mass. Most of what defines the Milky Way is invisible, existing in the form of dark matter and faint gas. The beauty we see is a thin surface over a hidden foundation. The bar, arms, bulge, and halo continue their roles. Gas flows inward, stars ignite and die. The black hole grows, and dark matter holds all in place. The Milky Way is now a mature, barred spiral galaxy, its form established, its rhythm steady. It will continue in this state for billions of years, a quiet beacon of light and motion drifting through the cosmic dark. The Milky Way enters a long Middle Age in which its large-scale shape changes little from one rotation to the next. Yet within this calm outline every part continues to move, mix and renew. The bar and the spiral pattern set up resonances that shift stars across the disk without greatly increasing their random motions. This radial migration carries metal-rich stars outward and metal-poor stars inward, softening the chemical gradient that star formation would otherwise maintain. In this way, the disk becomes a palimpsest, its lines of metallicity and age overwritten by the slow traffic of orbits that trade angular momentum with waves. A fact stands here. Dynamical models and observations agree that resonances near the bar and near the corrotation of spiral patterns can displace stars by thousands of light-years over billions of years, while leaving the disk relatively cool. A poetic detail glints inside dense clouds that pass through an arm. Dust grains accumulate mantles of ice in dark interiors, and when a nearby cluster turns on, those mantles sublime and briefly perfume the gas with simple molecules, a faint chemistry that will seed more complex recipes later. The quiet mystery concerns how strongly migration has sculpted the present relation between stellar age and composition in the solar neighbourhood. Some stars old and metal-rich may have been born in the inner galaxy and wandered outward. Some young and relatively metal-poor may have drifted inward from the outskirts. The balance between this churning and the history of gas inflow remains uncertain, and the uncertainty lingers like a shadow at the edge of every diagram. The bar continues to guide gas toward the inner few thousand light-years, where it collects in rings and lanes and forms stars in pulses. At the same time, the spiral pattern compresses gas along its crests, igniting clusters whose brilliant members live briefly and die, returning metals to the interstellar medium. Between the arms, older stars drift in quieter lanes. The disk as a whole grows thinner where the gas has had time to settle, yet in the distant outskirts the disk flares, thickening with radius as orbits feel the weaker grip of the central mass and the tug of the halo. The outer hydrogen layer is warped, tilting above and below the midplane, likely shaped by tides from satellites and by the lopsided pull of the dark halo. To an edge-on view, the warp is a slight smile drawn across the face of the galaxy. Streams in the halo continue their slow orbits. One wide ribbon belongs to a dwarf long since dissolved, another narrow stream still points back to a surviving companion. Globular clusters cross these paths, dense knots that shed a few stars on each perigalactic pass, leaving faint streaks that fade into the background light. The bar, exchanging angular momentum with the outer disk and with the dark halo, may slow and lengthen across time. Near its ends, resonances seed the beginnings of spiral arms, while nearer the center gas piles into a tight ring that forms stars even in the crowded bulge. The black hole at the very center remains mostly quiet, but on occasion a new supply of gas reaches its vicinity and it flares, adding heat and structure to the inner environment before returning to silence. A star like the Sun forms in one of the mid-radius rings within a cloud that is no longer primitive. Its gas carries iron and silicon from countless supernovae, carbon and oxygen from ancient giants, and trace elements from many channels. Around the new star, a disk feeds the growth of planets. Within that disk, calcium and aluminum-rich inclusions condense early and lock a timestamp into stone, while pebbles drift inward and pile up where gas drag slows them, building the cores of future worlds. Presolar grains, older than the star itself, survive as tiny relics inside some rocks, a delicate testament that the galaxy is a single recycling system across time. 3 soft ironies gather and drift. The disk looks permanent from afar, yet a single star can migrate across it like a wanderer who never senses the journey. Chemical gradients appear authoritative when averaged over rings, yet any given star may contradict the local pattern because its birthplace lies elsewhere. The warp seems like a flaw in symmetry, yet it is a signature of the galaxy listening to its surroundings and remaining in equilibrium with them. The outer reaches keep their slow conversation with companions. Tides from the small and large Magellanic clouds and from other dwarfs ruffle the outskirts, raising waves that travel inward and outward through the disk. Some waves stir gas and help to form stars. Others simply carry energy that slowly dissipates. The halo of dark matter, still unseen, remains the governing weight behind these motions. Its gravity is recorded in the nearly flat rotation speed of the outer disk, without which the luminous matter would not hold together. Whether the halo is made of a particle yet to be discovered or of something subtler remains open, and that ignorance is a steady invitation to humility inside an otherwise well-drawn picture. The chemical story continues to unfold. In the inner disk, the ratio of alpha elements to iron falls as time passes, because long-lived progenitors finally return iron to the gas, while oxygen and magnesium from short-lived progenitors had arrived earlier. In the outer disk, where star formation proceeds more gently, different balances emerge. Migration mixes these patterns like pages shuffled by a breeze so that any one stellar spectrum reads as a combined memory of birth and journey. A gentle analogy helps the mind hold the whole. The galaxy is a tidal marsh at slack water, broad and still in outline, yet at the surface channels switch direction, eddies move silt, and quiet inflows replace what evaporation and outflow remove. What endures is not a barrier against change but a balance of it. A second fact anchors the epoch. The global rate of star formation in the universe has declined from its ancient peak, yet the Milky Way continues at a moderate pace, sustained by inflow from its halo and from minor mergers and regulated by outflows that loft material into a fountain above the plane before it falls back. The Sun's birth is only one episode of many, and like other episodes it is prepared by older deaths and followed by new creations. Timescales remain immense. One orbital period at the Sun's radius spans more than 200 million years, long enough for an arm to pass, for a cluster to form and loosen, and for a migrating star to change its mean radius by thousands of light years. Yet to a distant watcher, the Milky Way would look unchanged across many such turns. A pale band pinned to the night only took a few 100 million years to write the chemical preface to a planetary system, which to the galaxy is a quick chapter, only took a few billion years to grow a bar strong enough to move stars without breaking the disk, which to the universe is ordinary, only took one quiet sequence of compressions to form a star like the Sun, which to its planets will feel like the definition of stability. The bar, the arms, the warp, the halo, and the hidden scaffold of dark matter continue to share a long breath. Gas moves inward along lanes, stars kindle and fade. Feedback lifts and returns material, and migration rearranges the long-lived population with each passing resonance. The Milky Way holds its shape not by resisting change, but by being a structure whose identity is the sum of changes. It is old enough to seem serene, young enough to keep forming stars, and balanced enough that permanence and impermanence are the same description viewed at different distances. The sun takes shape within a crowded nursery of gas and dust in the middle reaches of the disk, not at the blazing centre and not at the faint rim, but along a spiral lane where compression and quiet alternate. A cold cloud cools further, fragments, and collapses. Inside one fragment, a protostar gathers a thin disk around it. In that disk, dust grains collide and cling. Pebbles drift inward and settle where the headwind weakens, and in those gentle bands the seeds of planets take hold. Within only a few tens of millions of years, the young system is arranged. Rocky worlds circle close, giant planets anchor the outer lanes, and a halo of comets crowds the far edge. The open cluster that cradles the newborn sun is bright and brief, its massive blue stars sculpting cavities, while smaller red stars glow like embers along the darkness. The cluster loosens quickly. As gas is blown away by radiation and winds, gravity cannot hold the stars together. They drift apart and become field stars, carried off by the general rotation of the galaxy until the family is a memory only chemistry can recall. A steady fact belongs here. Stars like the Sun usually form in clusters inside dense molecular clouds, and most such clusters dissolve within a small fraction of a billion years. The solar system likely began within one of these dissolving families inside a spiral arm of the Milky Way. A lesser-known poetic detail glints inside ancient stones. Calcium and aluminum-rich inclusions in primitive meteorites record the earliest heat in the disk, while tiny pre-solar grains inside other fragments carry isotopic signatures older than the Sun, ash from long-dead stars that survived into a new world. In polar snows and deep-sea sediments, micrometeorites still fall and preserve that same stardust, a soft whisper of the galaxy touching Earth. A quiet mystery threads the nursery. Short-lived radionuclides such as aluminum-26 appear in the earlier solids of the solar system, hinting that a nearby massive star may have seeded the disk shortly before the planets formed. Did a supernova trigger the collapse of the parent cloud and salt the disk with those atoms? Or did winds from a giant star carry them in? Or did irradiation within the disk itself make them? Evidence allows several paths, and the balance among them remains unsettled. The Sun settles into an orbit around the galactic centre at a middle radius. It circles once every few 100 million years, rising and dipping through the thin plane with a slow vertical sway. Over billions of years, resonances with the spiral pattern and with the bar shift its average radius. The migration is gentle rather than violent, a trade of angular momentum that moves a star across thousands of light years while leaving its orbit cool. In this way, a star born slightly nearer the centre can be found later in a calmer ring, and a star born slightly farther out can wander inward, each carrying the chemical accent of its birthplace into a different neighbourhood. Three ironies gather softly. The stable planetary order that feels so quiet is born inside a cluster that dissolves almost at once. The materials that make a temperate world arrive through the violent deaths of massive stars. The Sun, which seems anchored, is a migrant that forgets its birthplace while keeping the chemistry of that place within it. The bar at the center lengthens and slows as it exchanges angular momentum with the outer disk and with the dark halo. Near the ends of the bar, resonances stir the inner spiral arms and gather gas into rings that form stars. Farther out, the arms remain as moving compressions that brighten where clouds collapse and then fade where the pattern passes. Between the arms, older stars drift in quieter lanes, and the disk keeps its thinness by allowing turbulence to settle and motions to align. In the halo, the long memory of assembly continues to circle. Streams from dissolved dwarfs ribbon the outskirts. Some streams are so faint that only the most patient surveys will map them. Others are almost bright enough to trace by eye from a dark world. Globular clusters cross these paths and shed a few stars with each close pass, writing delicate streaks into the sky of the halo. The large and small Magellanic clouds begin their slow dance with the Milky Way, trailed by a river of gas that arcs across the southern reaches, a sign that companionship and tide still shape the rim. Fact holds steady that the rotation speed of the Milky Way remains nearly flat far beyond the bright disk, a sign that most of the mass lives in an invisible halo. That unseen mass keeps the outer disk from flying apart and anchors the paths of the streams. Its precise nature remains unknown, and that ignorance sits, patient and intact, inside an otherwise well-drawn picture. Near the centre, the black hole grows by slow accretion and by occasional meals of gas clouds and passing stars. It spends long stretches quiet, but now and then it brightens and launches energy into the surrounding medium. Later ages will reveal giant lobes of hard light rising above and below the plane, monuments to a past episode when the nucleus breathed more strongly. Even these outbursts are gentle in the galactic accounting, brief ripples in a sea that mostly rests. The chemical story of the disk becomes layered. In the inner regions, where star formation is brisk, the interstellar medium grows rich in heavy elements. In the outskirts, enrichment lags. Radial migration smears these gradients, so that a neighbourhood like the Sun's holds stars of the same age, but different compositions, and stars of the same composition but different ages. The disk reads like pages shuffled and read again, every spectrum a memory of birth mixed with the record of travel. A gentle analogy frames the era. The Milky Way is a vast library whose shelves seem fixed while the books drift. Each star is a volume that begins in one wing and ends in another, while the catalogue of chemistry inside tells both where it was printed and where it has wandered. The library appears orderly to a distant glance, yet the path of any one book is a quiet migration. Timescales remain kind. One circuit of the Sun's orbit spans more than 200 million years, long enough for entire mountain ranges to rise and erode on one of its worlds. Yet to the galaxy, a single turn is only the tick of a very slow clock. Only took a few 100 million years for the cluster that birthed the Sun to dissolve, and that brevity shaped a system that would endure. Only took a handful of passing resonances to draw the Sun outward or inward by several thousand light years, and that slight wandering helped to mix the local sky without disturbing the disk. The bar turns, the arms breathe, the halo circles, the nucleus waits, and the dark matter scaffold holds its quiet weight. The Milky Way keeps its form not by resisting change, but by weaving change into a pattern that recurs. The Sun becomes one light among hundreds of billions, and yet its story fits within the larger script. In the steady rotation and the soft flicker of star formation, the galaxy carries on, serene in outline, intricate in detail, a place where permanence is the face of patient change. The Milky Way turns onward through billions of years, a barred spiral in full maturity, its form largely stable yet never fixed. The bar at its centre is now a strong structure, stretching thousands of light years across and driving gas toward the bulge. This inward flow fuels bursts of star formation in the crowded heart and nourishes the black hole that waits at the very centre. Sagittarius A is no longer a small seed, but a massive presence with millions of solar masses. It spends long stretches in silence, but in the past it has erupted, heating gas and sending outflows above and below the plane. The faint record of these events survives as bubbles and filaments that drift outward in X-rays and gamma rays, quiet witnesses to brief moments of fury in an otherwise calm life. The spiral arms reach outward, glowing with young clusters and bright nebulae. They are not fixed features, but moving compressions that pass through the disk, encouraging gas to collapse into stars. The arms remain luminous because they are continually refreshed, though any given star leaves them after a short passage. Between the arms lies the quiet majority of the disk, filled with older stars that shine more faintly but endure for billions of years. This combination gives the galaxy both brilliance and stability. A fact stands clear. Spiral galaxies sustain their forms through a balance of inflow, feedback and rotation. The Milky Way is no exception. Gas continues to trickle in from the halo, replenishing the star-forming regions. Feedback from supernovae and stellar winds prevents collapse from consuming gas too quickly. The bar and arms regulate the distribution of angular momentum. The whole remains coherent across time. A poetic detail glows in the faint warp of the outer disk. To an observer at the edge, the hydrogen layer bends gently upward on one side and downward on the other, like a wave frozen in place. This warp may be stirred by the tides of companions or by the shape of the dark halo itself. It is a soft asymmetry, visible only in patient surveys, but it adds grace to the edge of the galaxy. A mystery lingers in the role of satellite galaxies. The large and small Magellanic clouds orbit nearby, trailing a stream of gas across the southern sky. Their future merger with the Milky Way is inevitable, but how strongly they already shape its disk remains debated. Do they stir the spiral arms? Do they help maintain the warp? Their influence is clear in some respects but uncertain in others, and that uncertainty remains part of the galaxy's ongoing story. Three ironies weave into this age. The spiral arms that appear as permanent scaffolding are transient, always forming and dissolving. The luminous bursts of star formation that seem so abundant are supported by faint flows of hydrogen, nearly invisible to human eyes. The galaxy that looks serene from afar is kept alive by constant turbulence at every scale. The halo continues to circle with its long memory. Streams of stars wrap around the galaxy, relics of long-dissolved dwarfs. Globular clusters remain intact, dense with ancient stars, circling on orbits that take them far above and below the disk. Some clusters shed stars into faint trails that follow them like cometary tails, writing delicate lines into the halo. The outer halo is diffuse, its stars scattered and faint, but it remains part of the whole structure, bound by the dark matter that outweighs everything luminous. The bar grows slowly longer and stronger, transferring angular momentum outward. It reshapes the bulge, creating a boxy or peanut-shaped structure that is seen in many galaxies of the same type. The bulge is crowded with old stars but also enriched with younger ones formed from gas driven inward by the bar. It is a composite, recording both the galaxy's earliest times and its later secular evolution. A gentle analogy arises here. The Milky Way is like a great river delta. Streams of gas flow inward like channels, deposit their material at the core and build new land in the bulge. The bar is the guiding channel, the arms are the branching currents, and the halo is the open sea into which faint debris spreads. The delta grows and shifts but remains recognizably one body. The chemical enrichment continues. In the inner disk, metallicity rises steadily, while in the outskirts enrichment lags. Radial migration smears these gradients, moving stars across large distances. In the solar neighbourhood, the mix of stars shows this blending. Some are old and rich in metals, some young and relatively poor, a confusion that only detailed spectra can untangle. Each star is both a birthplace and a journey, and the disk as a whole is the sum of these layered stories. Timescales remain immense. One orbit of the galaxy's outermost stars takes nearly 1 billion years, long enough for entire epochs on any planet, yet only a brief note in the galaxy's song. The Sun and its system complete multiple turns during their lives, crossing spiral arms, drifting in and out of regions of higher density, yet the galaxy itself appears unchanged. Only took 6 to 7 billion years for the Milky Way to establish its present structure, which is swift by cosmic standards yet unfathomable in human time. Another irony emerges softly. The galaxy is at once fragile and robust. A single supernova reshapes its neighbourhood, yet billions of such events leave the grand form untouched. A single dwarf galaxy is shredded and absorbed, yet the spiral outline persists. Change is constant, yet continuity prevails. The Milky Way now shines with the light of hundreds of billions of stars. Its bar and arms give it grace, its bulge gives it depth, its halo gives it reach. Its black hole anchors the core, and its dark matter halo holds it all together. It has reached a balance that will last for billions more years, a phase of quiet majesty in which its structure remains steady, while its inner details are in constant motion. The Milky Way continues its slow rotation, a barred spiral galaxy luminous across the dark. The bar extends through the bulge, driving gas inward along its lanes and sustaining bursts of star formation near the centre. Sagittarius AA rests at the very core, a black hole of millions of solar masses. For most of its time it is quiet, yet its influence is permanent. Stars orbit it in tight ellipses, their paths a clear record of its gravity. When gas or a wandering star ventures too close, a flare of radiation briefly brightens the heart of the galaxy, before fading back into silence. The bulge glows with stars of many ages, most old and metal-rich, some younger, born from gas funneled inward. Its boxy shape reflects the strength of the bar, which redistributes angular momentum and shapes stellar orbits. Above and below the bulge extend faint bubbles, relics of earlier outbursts from the core still glowing in high-energy light. The disk lies broader and thinner than before. Spiral arms sweep outward, luminous with young stars and dark with dust lanes. Gas clouds collapse along the arms, forming clusters that briefly light the pattern. The arms are not permanent structures but density waves that move through the disk, compressing gas as they pass. They persist because they are continually renewed, stirred by resonances within the disk and by tides from companions. Between the arms drift older stars, a quieter majority that sustains the smooth light of the disk. The fact of spiral renewal is firm, yet the precise mechanism remains debated, a reminder that even in the familiar galaxy mysteries endure. A poetic detail lies in the way giant molecular clouds, many light years across, are shredded by newborn stars. Cavities expand as winds and radiation carve their surroundings, leaving behind shells and filaments that glow in faint light. These temporary sculptures dissolve within tens of millions of years, but while they last, they shape the view of the arms. A quiet mystery rests in the influence of the Magellanic Clouds. These satellite galaxies trail a long stream of gas that arcs across the halo. Their tides may stir the disk, shaping the warp and sustaining spiral structure, yet the details remain uncertain. How much do they contribute compared to internal instabilities? Observations suggest both matter, but the balance is unresolved. 3 soft ironies circle this age. The arms that look like solid architecture are ephemeral, shifting patterns refreshed by constant motion. The galaxy that seems serene requires constant turbulence to maintain itself. The greatest mass belongs to dark matter, unseen and silent, while the visible stars provide the beauty but not the weight. The halo continues its watch. Streams of stars orbit in long loops, remnants of dwarfs consumed long ago. Globular clusters survive, dense and ancient, orbiting far above and below the disk. Some clusters leave faint trails as stars escape, adding threads to the halo. The halo itself is diffuse, filled with stars of many origins, bound together by the vast invisible mass of dark matter. Without that mass, the outer disk would disperse. With it, the rotation curve remains flat, a signature of the unseen. The chemical enrichment of the disk deepens. Heavy elements accumulate in the gas, raising metallicity for new generations of stars. In the inner disk, enrichment is rapid. In the outer disk, slower star formation leaves the gas poorer. Radial migration blurs these gradients, moving stars across large distances. In the solar neighborhood, stars of many ages and compositions mingle, each one carrying the memory of its birthplace even if its orbit has wandered. A gentle analogy emerges. The Milky Way is like a vast loom weaving with threads of gas and stars. The arms are the shifting shuttles, the bar is the steady beam, and dark matter is the frame. Each pass of the shuttle adds a new thread. Each resonance shifts the pattern slightly, yet the fabric as a whole remains coherent, stretching across billions of years. The star formation rate of the galaxy is steady but not extreme. A few suns per year are born across the disk, balanced by the deaths of others. Supernovae enrich and stir the interstellar medium, lofting gas into fountains above the plane. That gas cools and falls back, feeding new stars. The cycle is continuous, neither exhausting nor idle, sustained by inflows from the halo and by gas stripped from companions. Timescales remain beyond measure. One orbit at the edge of the disk takes nearly 1 billion years. In that span, entire species rise and vanish on one planet, while the galaxy continues its motion unchanged. Only took 7 to 8 billion years for the Milky Way to acquire the form we see today. A bar, a bulge, a thin and thick disk, spiral arms, a wide halo, and an unseen scaffold of dark matter. To the universe this is swift. To us it is eternity. Another irony presents itself. The brightest stars, which give the arms their beauty, live the shortest lives, vanishing almost as soon as they appear. The dimmest red dwarfs, nearly invisible, persist for trillions of years, and will outlast the arms, the bar, and perhaps even the spiral form itself. The Milky Way now rests in a long phase of equilibrium. Its shape is set, its processes established. Gas continues to flow, stars continue to form and die, the halo continues to circle. The bar strengthens, the warp endures, the black hole grows in silence. The galaxy is no longer young, not yet old, but balanced in a middle age that will last for billions more years. It turns slowly, luminous against the void, serene in outline, restless in detail, always changing yet always itself. The Milky Way flows through cosmic time in the steadiness of rotation, its great spiral arms glowing faintly across the dark, its bulge dense at the centre, its bar a bridge between inner and outer. From a distance its structure looks fixed, yet closer inspection reveals constant change. Every star moves on its own orbit, every cloud collapses or disperses, every stream in the halo drifts in silence. What appears still is the balance of uncountable motions. Fact anchors this era. The Milky Way is a barred spiral galaxy of hundreds of billions of stars, spread across a disk 100,000 light-years wide and embedded in a dark matter halo far larger. Its total mass exceeds 1 trillion solar masses, most of it unseen. Observations of the rotation curve, star counts, and satellite motions confirm this hidden weight. The visible galaxy is only the luminous skin of a deeper body. A poetic detail lies in the faint ultraviolet glow that bathes the outer halo, light from hot young stars scattered by dust and gas. This glow is imperceptible to the human eye but can be traced by telescopes, a reminder that the galaxy radiates not only invisible light, but across the spectrum, each wavelength revealing a different facet of its story. The quiet mystery rests in the long-term stability of its spiral structure. Will the arms endure for billions more years, or are they transient, destined to dissolve and reform endlessly? Simulations and observations suggest both possibilities, and the answer may depend on the tides from satellite galaxies, the distribution of dark matter, and the feedback of star formation itself. The question remains open, a soft uncertainty within the broader consensus. 3 ironies accompany the galaxy's midlife. The arms that appear as scaffolds of permanence are fleeting patterns refreshed by constant flux. The brightest stars that define the arms vanish quickly, while the dimmest stars that fade into invisibility endure far longer. The grand symmetry admired from afar is created by countless disruptions, mergers, and explosions that never cease. The bar continues to lengthen and slow as it trades angular momentum with the outer disk and the dark halo. It funnels gas inward, sustaining star formation in the bulge and feeding the black hole. Sagittarius A grows gradually, usually quiet but occasionally flaring when matter approaches too closely. The relics of past outbursts still rise as bubbles above and below the plane, silent witnesses to the power of the core. In the disk, star formation remains steady. Giant molecular clouds collapse, forming clusters that shine briefly before dispersing. Nebulae glow in hydrogen emission, sculpted by radiation and winds from massive stars. Supernovae inject heavy elements and energy into the medium, lofting gas into fountains that rain back onto the plane. The cycle of creation and destruction sustains the galaxy, ensuring that star formation continues at a measured pace. In the halo, streams of stars trace the orbits of long-dissolved companions. Some streams are broad and diffuse, others narrow and sharp. Globular clusters remain, dense with ancient stars orbiting far beyond the disk. Each cluster is a fossil, a survivor from the earliest days, carrying with it the record of a different epoch. The Magellanic Clouds circle in the halo, trailed by the long stream of hydrogen known as the Magellanic Stream. Their interaction with the Milky Way stirs the outskirts, shaping the warp of the outer disk and perhaps sustaining the spiral structure. A gentle analogy emerges. The Milky Way is like a vast forest. Trees fall and decay, their matter recycled into soil, while new growth rises in their place. The forest looks unchanging when viewed from afar, yet every tree is in flux. So too with the galaxy. Stars are born and die. Gas flows in and out. Streams wander through the halo, yet the grand form endures. Chemical enrichment continues. Each generation of stars adds to the metallicity of the disk. In the inner regions, metallicity rises quickly, while in the outskirts it lags. Radial migration blurs the gradient, mixing stars across distances of thousands of light-years. The solar neighborhood holds stars of many ages and compositions, some older than the Sun, some younger, all orbiting together in the same general ring. Their chemistry tells the history of the galaxy in detail, recording the balance between enrichment and migration. Timescales remain incomprehensible, One orbit of the Sun around the galaxy takes more than 200 million years. In that span, entire mountain ranges can rise and vanish on a single planet. Yet the galaxy turns once, unnoticed. Only took 8 to 9 billion years for the Milky Way to reach its full maturity, which in cosmic time is no more than the middle of its life. Another irony appears softly. The galaxy is massive, yet most of its mass is unseen. It is bright, yet most of its light comes from stars that will soon die. It appears stable, yet its stability depends on constant change. The bar, arms, bulge, and halo continue their slow dance. Gas flows inward, stars ignite and fade, metals accumulate, and dark matter holds all together. The Milky Way is serene in outline, restless in detail, always changing yet always itself. The halo continues to remind the galaxy of its past. Each stream is a memory of a merger, each cluster a relic of early formation. The outer disk, warped and flared, listens to the tide of satellites and the pull of dark matter. The inner disk, thin and bright, shines with younger stars. The bulge glows with the density of old populations, while the bar channels new fuel into its heart. The black hole waits in silence, patient in its growth. A second analogy suggests itself. The galaxy is like a vast symphony. The bar is the deep, steady rhythm, the arms are the flowing melodies, the halo is the echo of past notes, and dark matter is the silent structure that holds the orchestra together. The music unfolds slowly, each phrase lasting hundreds of millions of years, yet the harmony persists. The Milky Way is no longer young, but not yet old. It has reached a steady balance, a phase of quiet majesty that will endure for billions more years. Its structure is established, its process is ongoing, its future shaped by the same forces that brought it here. It drifts through the universe luminous and calm, a barred spiral glowing softly against the darkness, a galaxy whose permanence is built from ceaseless change. The Milky Way moves deeper into its middle age, a barred spiral galaxy whose form is familiar yet whose details remain restless. The central bar stretches farther across the bulge, driving gas along its lanes into the inner regions where bursts of star formation flare. In the dense core, the black hole Sagittarius A continues to grow in silence, gaining mass from streams of gas and the occasional unlucky star. Most of the time it is quiescent, yet its gravity shapes the orbits of nearby stars, and past eruptions are preserved as giant lobes of radiation rising above and below the disk. The bulge shines with a mix of populations, many ancient, some younger, all crowded into random orbits that cross one another in the dense heart. The spiral arms sweep outward, glowing with new stars and glowing nebulum. They are not permanent fixtures, but patterns of density moving through the disk. Stars form within them, then drift away, leaving the arms always refreshed but never fixed. Dust lanes run along the inner edges of the arms, cold and dark, yet crucial because they shield molecules that cool the gas and allow collapse. Between the arms, the older stars drift in quieter orbits, providing the steady light of the disk. A fact is clear. The Milky Way continues to form a few suns' worth of stars each year, balanced by the deaths of others. This rate is modest compared to the peak of cosmic star formation billions of years earlier, yet it is steady enough to maintain the galaxy's glow. Supernovae enrich the medium with heavy elements, driving turbulence and lofting gas into fountains above the plane. That gas cools and falls back, feeding the cycle again. The galaxy breathes in this way, inhaling inflows from the halo, exhaling outflows from explosions, and sustaining equilibrium. A poetic detail lies in the faint warp of the outer disk. From afar it looks like a smile across the galaxy's edge, bending up on one side and down on the other. This warp may be stirred by the Magellanic Clouds or by the asymmetric shape of the dark matter halo. It is a small distortion compared to the whole, yet it gives grace to the rim and reminds us that even large structures are sensitive to subtle pulls. The quiet mystery rests in the long future of the Magellanic Clouds themselves. They orbit close, trailing the Magellanic stream of hydrogen across the southern sky. Will they merge with the Milky Way within a few billion years, stirring its disk and feeding its star formation? The answer is likely yes, but the timing and consequences are uncertain, depending on dark matter and orbital dynamics that remain only partly known. 3 soft ironies belong to this stage. The galaxy looks serene, yet turbulence in gas clouds is what sustains star formation. The most beautiful structures, the spiral arms, are the most fleeting, refreshed only by constant flux. The greatest influence on the galaxy's fate comes not from what is seen, but from dark matter, invisible and silent, yet holding everything together. The halo continues to carry the memory of the past. Streams of stars wrap around the disk, remnants of dwarfs torn apart by tides. Globular clusters remain intact, dense with ancient stars, orbiting on long paths far above and below the plane. Some clusters shed faint trails of stars, thin streaks that follow them through the halo. The outer halo is diffuse and vast, stretching hundreds of thousands of light years, its stars sparse but still bound to the galaxy's gravity. The bar grows stronger with time, trading angular momentum with the outer disk and halo. Its resonances shift stars across the disk, spreading populations and softening gradients. Near its ends, spiral arms begin, linking inner and outer structures. Gas piles into rings and lanes where resonances overlap, forming stars in bursts. The bulge is reshaped into a boxy form, evidence of the bar's influence on stellar orbits. Chemical enrichment continues across the disk. In the inner regions, metallicity is high, stars forming with abundant heavy elements. In the outskirts, enrichment lags, leaving some populations metal poor. Radial migration mixes these gradients, moving stars far from their birthplaces. In the solar neighbourhood, this mixing produces a range of compositions and ages, a confusion that carries the signature of both chemistry and dynamics. Timescales remain immense. One orbit of the Sun around the galactic centre takes more than 200 million years. In that time, mountains rise and erode on one planet. Ice ages come and go, civilizations appear and vanish, yet the galaxy completes only a single turn. To the galaxy, such events are less than a moment. Only took 9 to 10 billion years for the Milky Way to acquire its present balance, a span that to us is eternity, but to the universe is only middle age. Another irony lies in the contrast between stars. The bright blue stars that define the arms live only millions of years and vanish in explosions. The dim red dwarfs, nearly invisible, live for trillions of years and will outlast the galaxy's current form. The beauty of the Milky Way depends on the briefest lives, while its endurance rests on the faintest. The galaxy now rests in equilibrium. The bar channels gas inward, the arms renew themselves through density waves, the halo holds its streams and clusters, the black hole grows in silence, and dark matter holds all together. It is a mature barred spiral, luminous, balanced, and patient. Yet even in this stability, change is constant. Stars migrate, gas circulates, clusters dissolve, streams lengthen, and chemistry grows richer. A gentle analogy arises. The Milky Way is like an ancient city. Streets remain in place, buildings endure, but people move, markets open and close, and every detail changes with time. To the distant eye, the city is eternal. To those within it is alive with motion. So too with the galaxy, stable in outline, restless within, timeless in appearance, yet built from countless transient acts. The Milky Way drifts through space luminous and serene, a spiral glowing against the dark, a home whose permanence is only the patience of change. The Milky Way reaches into the present era, a barred spiral galaxy in long maturity, steady in form though every detail within it remains unsettled. The bar dominates the inner disk, stretching across the bulge and moving gas toward the center. This inward flow sustains clusters of new stars in the heart, keeps the bulge alive with recent generations, and offers fuel to the black hole at the core. Sagittarius Ace is massive now, millions of times the mass of the Sun, usually quiet but occasionally active. In the past it has flared, releasing energy that carved great bubbles rising above and below the plane. These structures linger even now, faint arcs of high-energy radiation that show how even the stillest centers sometimes erupt. The bulge itself glows with a mix of stellar populations, many ancient, some younger, their metallicities varied. The bar reshapes their orbits into a boxy form, evidence of its long influence. Beyond the bulge, the spiral arms curl outward. They are filled with young stars and nebulae, their light outlining the pattern. Dust lanes shadow the arms, dark rivers across the glow. Stars form within them in dense clusters, then drift away, leaving the arms to be renewed by new generations. The arms are transient yet persistent, their beauty maintained by flux. Between them, older stars shine more evenly, forming the background glow of the disk. The fact remains, the Milky Way forms stars at a modest rate of a few suns per year. It has enough gas to continue this for billions of years, though gradually the supply will diminish. Supernovae and winds enrich the gas with heavy elements, pushing some material into fountains above the disk before it rains back down. This circulation keeps the cycle in balance, preventing both exhaustion and stagnation. A poetic detail lies in the long hydrogen stream of the Magellanic Clouds, a ribbon that wraps across the halo. This stream is evidence of interaction, a river of gas torn from satellites by tides. It feeds the galaxy even as it signals future merger. The clouds themselves orbit nearby, bright companions in the sky of the southern hemisphere, bound to join the Milky Way more fully in ages ahead. A mystery persists in the dark matter halo. Its mass holds the galaxy together, shaping the rotation curve and anchoring the disk, yet its nature is still unknown. Is it made of particles beyond current physics, or is it a sign that gravity behaves differently on the larger scales? For now it is invisible, yet undeniable, the skeleton on which the luminous body rests. 3 ironies attend this age. The Milky Way's glow depends on massive stars that live only briefly, so its beauty is drawn from fragility. The galaxy appears calm in outline, yet it is maintained by turbulence at every scale. The structure seems permanent, yet it exists only because of unseen matter whose nature remains mysterious. In the halo, streams of stars continue their long orbits. They are relics of ancient mergers, fossil rivers circling still. Globular clusters remain intact, dense and ancient, some shedding faint trails that add new threads to the halo. The outer disk flares and warps, shaped by tides and by the dark halo's form. The warp gives the rim a gentle curve, an asymmetry visible only with patience, but persistent across billions of years. Chemical enrichment continues, raising metallicity in the inner disk while the outer disk lags behind. Migration of stars blurs the gradients, mixing populations across wide ranges. In the solar neighborhood, stars of many ages and compositions share the same sky. each one carrying the chemistry of its birthplace and the memory of its path. The Sun itself circles with them, completing an orbit every 200 million years, drifting slowly in and out of spiral arms, its path shaped by resonances and tides. A gentle analogy frames the whole. The Milky Way is like a great garden tended by gravity. Seeds of gas clouds sprout into stars, blossoms flare and fade, their ashes return as soil, and new growth rises again. The gardener is patient, its hand invisible, its harvest spread across billions of years. The beauty of the garden comes from transience, while its endurance comes from the balance of change. Timescales remain beyond ordinary measure. One orbit of the galaxy's rim is nearly 1 billion years. In that time, continents can wander across a planet. Oceans can open and close. Species can rise and fall. Yet to the galaxy, such an orbit is only a note in its long music. Only took 10 to 11 billion years for the Milky Way to reach the state we see now, which is swift by cosmic standards, yet longer than human minds can truly grasp. Another irony stands quietly. The galaxy looks unique to us because it is our home, yet across the universe there are countless barred spirals with similar forms, each luminous and calm, each made of countless stars that live and die without notice. The Milky Way is both singular and ordinary, a mirror of universal processes and a cradle of one particular history. The galaxy drifts through its present with serenity. The bar turns, the arms sweep, the halo circles, the black hole rests. Gas flows inward and outward, stars form and die, metals accumulate, dark matter holds the whole together. The Milky Way has become itself, a barred spiral of quiet majesty, luminous against the void. It will remain in this form for billions more years, until new mergers reshape it and time carries it into a different destiny. For now it endures, balanced and patient, permanent only because it is always changing.